Today, we're diving deep into one of the most powerful concepts in cognitive science, metacognition. This is the scientific study of how we think about our own thinking, and understanding it can revolutionize how you learn and solve problems. Let's start with the fundamental question: what exactly is metacognition? Metacognition is your brain's remarkable ability to step back and observe its own processes. It's like having an internal supervisor monitoring your mental operations. Scientists break metacognition into two core components. First is metacognitive knowledge, which is what you know about how you think. Second is metacognitive regulation, which is how you control and adjust your thinking. These two components work together constantly. Your knowledge informs how you regulate, and your regulation experiences update your knowledge. It's a continuous feedback loop. Let me give you a powerful analogy to understand metacognition. Think of your brain as an orchestra. You have different sections: memory playing its part, attention keeping rhythm, reasoning working through melodies. Metacognition is the conductor, coordinating all these processes, deciding when each should be louder or softer, faster or slower. Just like a conductor doesn't play the instruments, but shapes the entire performance, metacognition doesn't do the thinking itself, but it orchestrates how all your cognitive processes work together. Now let's break down the three critical phases of metacognitive regulation. This is where the science gets really practical. Phase 1 is planning. Before you dive into any problem, your metacognitive system asks, what do I already know? What's my goal? What strategy should I use? This pre-thinking phase is crucial. Phase 2 is monitoring. While you're working, you continuously check. Am I making progress? Is this strategy working? Do I need to adjust? This real-time feedback is what separates experts from novices. Phase 3 is evaluation. After completing a task, you reflect. Did my strategy work? What would I do differently next time? How can I improve? This reflection solidifies learning. These three phases form a continuous cycle. Each time you complete this cycle, you become more effective at learning and problem solving. Now you might be asking, how much does metacognition actually help? Can we quantify its impact? Let's look at the research. Multiple meta-analyses in educational psychology have measured the impact of metacognitive training. The results are striking. A comprehensive meta-analysis by Dignath and Butner found that metacognitive interventions produce an effect size of Cohen's d equals 0.69. For those not familiar with statistics, this is considered a medium to large effect. But what does that actually mean in practice? Let's do a back-of-the-envelope calculation. Imagine two groups of students learning the same material. The control group, using standard study methods, achieves a mean score of 70% with a standard deviation of 10%. The metacognitive training group would score approximately 70% plus 0.69 times 10%, which equals 76.9%. That's nearly a 7 percentage point improvement. In many academic contexts, a 7 percentage point improvement could mean the difference between a B and an A, or between passing and failing a challenging course. Now let's examine the specific mechanisms by which metacognition accelerates learning. This is where neuroscience meets practical application. First mechanism: efficient resource allocation. Your brain has limited cognitive resources, attention and working memory. Metacognition helps you allocate these resources optimally. Studies show that without metacognition, learners waste cognitive resources on irrelevant details. With metacognition, they focus precisely on gaps in understanding, making learning approximately 3 times more efficient. Second mechanism: rapid error detection and correction. Metacognition acts like a quality control system. Consider reading comprehension. Poor readers often continue reading even when they don't understand. Their metacognitive monitoring is weak. Skilled readers constantly monitor their comprehension. The moment confusion arises, they detect it, pause, and employ fix-up strategies like rereading or seeking clarification. This metacognitive awareness dramatically improves learning efficiency. Research by Presley and Afterbach found that skilled readers pause to monitor comprehension approximately 40% more frequently than poor readers. This extra monitoring time actually saves time overall by preventing misunderstanding. Now let's explore one of the most important applications of metacognition: avoiding cognitive biases. This is where metacognition becomes a tool for clearer thinking. Human cognition is riddled with systematic biases. These aren't random errors, they're predictable flaws in how we process information. Metacognition is our best defense. Let's examine confirmation bias, one of the most pervasive cognitive errors. Confirmation bias is our tendency to seek, interpret, and remember information that confirms our pre-existing beliefs while ignoring contradictory evidence. Without metacognitive awareness, you naturally gravitate towards supporting evidence and dismiss contradicting evidence. Your brain does this automatically, outside conscious awareness. The metacognitive intervention is to deliberately and consciously seek disconfirming evidence. You force yourself to ask, what would prove me wrong? What am I not seeing? You might wonder, how effective is this metacognitive debiasing? Can we measure it? The classic study by Lord, Lepper, and Preston tested a simple metacognitive strategy called Consider the Opposite. Participants who were instructed to actively consider the opposite viewpoint showed bias reduction ranging from 31% to 58% compared to control groups. That's a substantial improvement from a simple metacognitive prompt. Now let's discuss one of the most fascinating intersections of metacognition and bias, the Dunning-Kruger effect. The Dunning-Kruger effect describes how people with low competence in a domain dramatically overestimate their ability, while experts often underestimate theirs. Beginners have high confidence but low skill. As you learn more, you realize how much you don't know, confidence drops. Eventually, experts develop calibrated confidence that matches their actual ability. Dunning and Kruger's key insight was that the same skills needed to be competent are the same skills needed to evaluate competence. If you lack skill, you also lack the metacognitive ability to recognize your lack of skill. The solution is deliberate metacognitive calibration. After making predictions or judgments, actively seek feedback. Compare your predictions to reality. This trains your metacognitive accuracy. Now let's apply metacognition to designing better problem-solving strategies. This is where theory becomes practical power. Experts across domains, from physics to chess to programming, use remarkably similar metacognitive strategies. Step 1. Experts spend significantly more time on problem representation before attempting solutions. Studies show experts spend 30 to 40% of total problem-solving time just understanding and representing the problem. Novices rush to solve immediately, spending maybe 5% of time planning. Experts invest 40% upfront in understanding. This seems slower, but actually reduces total problem-solving time by avoiding false starts. Step 2. Experts engage in continuous metacognitive questioning. They constantly ask themselves questions about their process. What type of problem is this? Have I seen something similar? What are my assumptions? What could go wrong with this approach? Am I actually making progress or just spinning my wheels? Step 3. Experts set specific checkpoints to evaluate strategy effectiveness. If a strategy isn't working, they switch rather than persisting stubbornly. Research on expert problem solvers shows they switch strategies an average of 3.2 times per complex problem. Novices switch only 0.8 times on average. They tend to persist with initial approaches even when failing. This inflexibility is a metacognitive deficit. Let me give you a concrete metacognitive protocol you can implement immediately. This is based on extensive research in educational psychology. It's called the SOAR protocol: select, organize, associate, and regulate. Select means consciously choosing what information to focus on. Organize means actively structuring that information. Associate means connecting it to prior knowledge. Regulate means continuously monitoring your understanding and adjusting. Students trained in the SOAR protocol show approximately 40% better retention compared to passive studying, according to multiple studies. Now let's dive into the neuroscience. What's happening in your brain when you engage in metacognition? Metacognition primarily involves the prefrontal cortex, particularly the anterior prefrontal cortex. This is the most recently evolved part of the human brain. The prefrontal cortex acts as an executive control system, monitoring and regulating activity in other brain regions. It's literally your brain watching it. Functional MRI studies consistently show increased prefrontal cortex activation when people engage in metacognitive monitoring tasks compared to automatic processing. Interestingly, metacognitive ability develops relatively late. Children under age 7 show limited metacognitive monitoring. It continues developing through adolescence as the prefrontal cortex matures. But here's the crucial point. Metacognition is highly trainable at any age. Your metacognitive abilities can improve with deliberate practice, even in adulthood. Let's do one more quantitative analysis. What's the cumulative advantage of improved metacognition over time? Imagine you're learning something new, let's say a programming language, or a scientific field. Let's say a standard learner without metacognitive training acquires 1 unit of knowledge per week. A metacognitively trained learner, based on the research we discussed, might acquire 1.2 units per week. That's a 20% improvement, which is actually conservative based on the studies. Now let's calculate the difference after 1 year of consistent learning. The standard learner after 52 weeks has acquired 52 units of knowledge. The metacognitive learner has acquired 62.4 units. That's 10.4 additional units, a 20% advantage. But here's where it gets interesting. The metacognitive learner now has a stronger foundation. In year 2, they can learn even faster because learning compounds. If we model this compounding effect, after 5 years, the metacognitive learner might have acquired 2.5 times as much functional knowledge. The gap widens exponentially. Now let's discuss common metacognitive failures. Understanding where metacognition breaks down helps you avoid these traps. Failure 1. The illusion of understanding. This is when you think you understand something, but actually don't. It's also called the fluency illusion. A classic example is rereading. When you reread material, it feels familiar and fluent. Your brain mistakes this fluency for understanding. But tests show rereading produces minimal learning gains. Self-testing feels more difficult and less fluent, so people avoid it. But testing is far more effective for learning. Good metacognition means recognizing that difficulty during learning often indicates effective learning, not ineffective learning. Failure 2. The planning fallacy. We systematically underestimate how long tasks will take. This is a metacognitive error in predicting our own performance. Studies show people typically underestimate task duration by 50 to 200%. A task you think will take 1 hour might actually take 2 to 3 hours. The metacognitive correction is reference class forecasting. Instead of asking how long this specific task will take, ask how long similar tasks have taken in the past. Use actual data, not optimistic intuition. Failure 3. Overconfidence in memory. People dramatically overestimate how much they'll remember without review. The classic Ebbinghaus forgetting curve shows you forget approximately 50% of new information within 1 day without review, and 70% within 1 week. After just 1 day, you retain only about 50%. After 1 week, only 30% remains. Most people don't metacognitively anticipate this rapid decay. The solution is metacognitively designing your learning around this reality. Use spaced repetition systems that schedule reviews based on the forgetting curve. Let me give you concrete practices to develop your metacognition starting today. Practice 1. The 2-minute metacognitive check. After any learning session or problem-solving attempt, spend exactly 2 minutes reflecting. Ask yourself 3 questions. What worked well? What didn't work? What will I do differently next time? Write down brief answers. This simple practice dramatically improves metacognitive accuracy. Practice 2. Create prediction and feedback loops. Before tests, presentations, or problem-solving sessions, explicitly predict your performance. Rate your confidence on a scale from 0 to 100%. Then compare your prediction to actual results. Track this over time. Research shows metacognitive calibration improves substantially after just 10 to 20 trials of prediction and feedback. You're training your internal monitoring system. Practice 3. Deliberately seek difficulty during learning. If something feels too easy, you're probably not learning optimally. Bjork's research on desirable difficulties shows that introducing challenges during learning, like spacing, interleaving, or testing, feels harder but produces much better long-term retention. Practice 4. Use the Feynman technique. Try to explain concepts in simple terms as if teaching someone else. This forces metacognitive awareness of gaps in understanding. If you can't explain something simply, that's metacognitive feedback that you don't truly understand it yet. This technique is named after physicist Richard Feynman, who was famous for his clear explanations. Finally, let's talk about cultivating a metacognitive mindset. This is about identity and approach, not just techniques. The metacognitive mindset involves shifting from a performance orientation to a learning orientation. You view challenges as opportunities to improve your thinking processes, not just as tests of ability. This connects to Carol Dweck's growth mindset research. People with growth mindsets see abilities as developable through effort and strategy. This is fundamentally a metacognitive perspective. In the metacognitive mindset, you embrace confusion as a valuable signal. Confusion indicates you're at the edge of your understanding, which is exactly where learning happens. Fixed mindset interprets confusion as evidence of inadequacy. Metacognitive mindset interprets it as valuable information about where to focus learning effort. Let me summarize the key scientific principles we've covered about metacognition. Metacognition is your brain's executive control system, monitoring and regulating how you think, learn, and solve problems. The research consistently shows substantial benefits, with effect sizes ranging from 20 to 70% improvements in learning and problem solving. It works through 3 main mechanisms: efficient resource allocation, rapid error detection and correction, and flexible strategy selection. Metacognition serves as a powerful defense against cognitive biases by making your thinking processes transparent and subject to conscious evaluation. Perhaps most importantly, metacognition is highly trainable. With deliberate practice of metacognitive strategies, you can substantially improve your thinking effectiveness. If I could teach only one skill to accelerate learning and problem solving, it would be metacognition. Learning how to learn, thinking about thinking, these meta-level skills multiply the effectiveness of everything else you do intellectually.